This video is going to show you how to calculate the pH for the solution of a solution of a weak base. So we've got a concentration, we have a substance, and this substance is ammonia. And we know that ammonia is weak because it is not a group 1 or scab hydroxide. We also know that it's weak because a Kb is given. So just like when we did the acids, the first thing we're going to do is we're going to write the dissociation reaction. Now for bases, you're going to want to write water with them because water is going to donate the proton that the base will then accept. And that will give us ammonium and hydroxide ion. So like we did last time, we're going to set up an ice table, fence under the arrow, and then we are going to include our given, and we're not including water because it's not part of the expression. Ammonium and hydroxide are going to be 0 to start because neither are present, and then because we have a Kb, we can write the expression, the equilibrium expression for that. So it's going to be concentration of ammonium times concentration of hydroxide divided by concentration of ammonia, and I'm not including water. So because that Kb is given, 1.8 times 10 to the negative fifth, we can use x because we have no equilibrium concentrations. So the side with the zeros will go up by x. The reactant side will go down by x. We get 15 minus x, x, and x. So when we substitute, both of these are the same, so that's x squared divided by the concentration of ammonia, which is 15 minus x. Now, just like when we did it with the acids, and you can use the quadratic formula to solve, or when that exponent is -5 or smaller, you can approximate as long as your Kb times 100 is less than or equal to the initial concentration of the base in this case. And if we take this times 100, it is way smaller than that. So we're going to go ahead and approximate. When I approximate, I am saying that x is so small that it's essentially 0, not making this x 0, just the one that's added on or subtracted off. So basically, we have 1.8 times 10 to the negative fifth equals x squared over 15. This is like it's over 1, so we are going to cross multiply and then solve for x. So our, x squared is equal to 2.7 times 10 to the negative fourth. I'm going to do the square root of that, which will give us x equals, okay, we've got to check sig figs. We have 3 and we have 2, so I'm going to use 2.016. That is molar because it's a concentration. That gives us the concentration of ammonium. Also gives us the concentration of hydroxide. We could determine the concentration of ammonia if we wanted it, but we're not worried about that right now. So to get to pH, I have to remember that this is hydroxide ion concentration. So I can do pOH first. Let's do it that way on this one, and then I'll do it a different way on the other one. So pOH is going to be the negative log of the hydroxide ion concentration. So when I do negative log of that number, I get 2 sig figs here. I need 2 numbers past the decimal. So 1.78. And then to get pH, I do 14 minus 1.78, which will give us 12 point, and remember this is 14.00, so I still need 2 numbers past the decimal, so this is going to be 12.22. Does that make sense? pH above 8 for a weak base. Yes. Okay, so this is another example. Here they're giving you pH right here. They give you initial concentration, and then they're talking about something called hydrazine, and they want to know what the KB is. So you probably don't know what this is, so it's definitely not a group 1 or a scab hydroxide, so it's got to be weak, plus there's a KB, so that's a clue. So the first thing we need to do is we need to write a dissociation reaction, and we're going to put the weak base plus water, and water is going to donate a proton because this is a base, and I know bases are proton acceptors. So when you're in a situation like this where you're like, I don't know what this thing is, I don't know how to write this, think about what you do know and about the fact that bases accept protons. So water is going to give this proton to the base. Write the base as it is. So, H2, NNH, and then you're adding an additional hydrogen here. Now, this was neutral. You just added a proton, so this is going to be plus. And then you get hydroxide. So, initial, an ice chart, Xing out water because it's not part of the expression. And then I'm substituting what I know. 0.025 molar solution of hydrazine, neither of these to start, and read the problem, and I need to find the KB, and I've got pH of 10.94. So from pH I can find hydrogen ion concentration. I will get that by doing 10 to the negative pH. So if I do 10 to the negative 10.94, I get 1.15 times 10 to the negative 11. Now this has two numbers past the decimal, so I would have two significant figures, but I'm not going to worry about that until the next step. That gives me hydrogen ion concentration, but that's not part of my reaction. I have hydroxide here, so I need to go, I'm going to use Kw equals hydrogen ion concentration times hydroxide ion concentration. So Kw, which is 1 times 10 to the negative 14th, is going to equal 1.15 times 10 to the negative 11th times my hydroxide ion concentration. So I am taking both sides and I am dividing by 1.15 times 10 to the negative 11th, and I get 8.70 times 10 to the negative 4th molar. So that's this concentration at equilibrium. So I want to fill that in on my equilibrium line. So 8.70 times 10 to the negative 4th. Okay. So what that means is that hydroxide went up by that same value. Because this is a 1-to-1 molar ratio, the other product also went up by the same amount, and hydrazine went down by that same quantity. So on the equilibrium line, both of our products have a concentration of 8.7 times 10 to the negative 4th, and hydrazine has a concentration of 0.02413, and these are all molar. Okay, now what I need to do is solve for Kb, and I don't want all of this because I need a place to solve, so I'm going to get rid of that. Okay, so I'm going to say KB is equal to, this would be if I were writing the expression. So I'm doing concentration of products divided by concentration of reactants, but I'm not including water because water is a pure liquid. These two are both the same, so I'm going to square those. And then I'm dividing by 0.02413. Okay, when we solve for that, we get a KB that is equal to 3.13, so 3.1 times 10 to the negative fifth. Okay, one more quick example if you need one more. If you don't, you can stop watching. Okay, so we want pH. We have methylamine, and it's got a KB. So I know that methylamine is weak. I'm going to have to write an equilibrium reaction for this. It's a weak base, so I have to have water. I don't know what to do with this because I've never seen it before. So it says it's a weak, this is telling me that I've got a weak base. If I've got a KB, I know that that's a weak base. So I'm going to take the hydrogen that's at the front of the water, and that proton is going to be donated to this methylamine. So what you have, remember these hydrogens are associated with the carbon. And now instead of 2 here, you're going to have 3, and you are adding a plus, and then hydroxide is left over. So I'm setting up my ice chart, Xing out water because it is a pure liquid and is not included, and now I'm entering my given. Do not have a given concentration for either of these, so they both get 0. And because I have a KB, I could really write the expression. So I'd have this ion and hydroxide concentrations divided by the methylamine concentration. I have no equilibrium concentration, so that tells me I can use X. The reactant side will go down by X, product side will go up by X. So I'm going to substitute. So 4.38 times 10 to the negative 4 is going to equal, these two are the same, x squared divided by 0.50 minus x. Okay, if this is 10 to the negative 4th, we don't want to usually approximate. However, if I take this times 100, so KB times 100, that is still less than the initial concentration. So I'm going to approximate. If you don't have to, you could do the quadratic. I'm just doing this because it's faster. That means that this x is 0, which essentially means that it is not there. So I'm going to do 4.38 times 10 to the negative 4th times 0.5. That will give us x squared equals 2.19 times 10 to the negative 4th. I'm going to take the square root of both sides, and I will get an x that is equal to 0.0148 molar. If I look up here, that's my x, but I have to pay attention to the fact that this is hydroxide. So when I go to calculate pH, I can't just do negative log of this. So I'm going to do this differently because I told you I was going to. So I'm going to use KW. So I'm going to say that The hydrogen ion concentration of this solution is equal to 1 times 10 to the negative 14th, which is kW, divided by my hydroxide ion concentration, 0.0148. When I divide, I get 6.76 times 10 to the negative 13th. So then I can take this and I can say, let me get rid of this over here. So we've got room. Okay. So then I can do pH equals negative log of 6.76 times 10 to the negative 13th. Don't forget that negative log. And that gives me a pH of 12 point, okay, with sig figs, I have 2, so that means 2 digits after the decimal 12.17, which would make sense for a weak base.